that bother you? Okay, so this is section 1C, more Venn diagrams. And this is with number of elements. And one thing you'll notice as we go through this class is that I think this class always goes in like threes. So for each section, for each chapter, there's 3 sections. And usually what happens is the first section has all these definitions because it's introducing a brand new topic. So I have all these introductions. And hopefully that first homework of the section or the chapter will be fairly easy. As we go, it might get a little harder. And that is true with the first one, is that the first, especially because it's the first section of the class, we have a lot of definitions. Now we don't have that much because we've defined so much. Now we're just going through more complicated problems, but there will be review and that kind of thing. So that's kind of a heads up of how the class is structured, but the theme of 3 comes up a lot in this class just by the way it's structured. So I want to start with just going through some examples. Because we've already learned so much, we can just kind of review a little bit about what is going on. And I wish there was a copy and paste feature in this program, but I don't think there is. Okay, so no, I'm going to change this. I want to change this. Let's do 3 circles. 1, 2. That's not terrible. Let's call this A. Let's call this B. Let's call that C. Okay, so that's 12, 7, 9, 23. C is 11, 5. Probably write that 5 a little better. And 14. Okay, let's get a little more practice with identifying how this will work. So this is a Venn diagram that has numbers inside of it instead of elements. Okay, so this is considerably less abstract than what we've done before. In fact, to make this a little better, I'm going to put the number 19 out here. That will help us as well. So this is Venn diagram with numbers instead of just symbols or just the general idea. But if I asked you how many elements are inside A, what would you say? So what would you say? How many are inside A? So this is my A.
4.
4. Okay, so we have 23, 9, 7, and 12. But what if you added them together? So since they're numbers, I'm going to say that, not letters, but numbers, we can add these together, and that will be the sum of A. So I understand where 4 comes from. There's 4 like elements, but how many are in here? So let's say that this is 12 elements, 7 elements, 9 elements, 23 elements. Then what would you say? How many are inside A? Anyone? How many are inside A?
41.
41. I think that's close.
51.
51.
Oh, that's what I meant.
Yeah. Missed a 10 there. That's okay though. So if we said that, how many's in B? Well, we have 14, 7, 21, 9, 35. Okay. How many's in C? 23, 34, 37. 48. Okay, that's the easy stuff. Now, how many is in the intersection of A and B? A and B is right here. How many is that?
16.
16. Awesome. How many is in B and C? B and C is right here.
14.
14. Okay, trick question. How many is in C intersect B? I flipped the order. Does it matter? Is it the same number? C intersect B. This is the kind of stuff that always pops up in exams, right? It's that kind of stuff that shows up when it shouldn't show up. So let's go over it now. Does it matter if they're flipped? Is it the same intersection? Does the order matter? Is anyone brave enough to say?
I'll say no.
I agree with you. I think it doesn't matter. But it's good that we go over it now, so it's no big deal later. All right, what about C intersect A? What would that be? C intersect A. That would be here.
32.
32. It's another good one. Oh, what's this one? A intersect B intersect C. What is the intersection of all of them? What is the intersection of all of them? What's the one thing they haven't? Oh, there's one in the chat. Yeah, Lon says it's 9, and I agree. It's 9. That's what they have. 9. Okay. What about the union of all of them? A union B union C. If you want, use a calculator. Use your calculator. Calculator check. What's the union of all of them? How many is that? So the union of all 3 of them would be 81. Very good. Okay. Have we done enough easy ones? Nah. Let's do the universal set. How many's in everything? Now, I didn't catch you said the last one, but somebody said 81. They've already done the work for us. So all of this is 81. We have 19 to go. How many's in the whole thing? The universal set.
100.
100. All right. Let's get a little bit more interesting. Let's do change color. A intersect B complement. A intersect B complement. I always think of this as A minus B. That's how I think of it. But what would that be? Where is that? How much would that be? A intersect B complement. This is the part of A that has nothing to do with B. Part of A that has nothing to do with B.
Is it 46?
I think that's a little too much. Little high.
16.
Little low. Wait. Wait. Maybe I'm off. Maybe I messed up. The part of A that has nothing to do with B, right here. Did I mess up? Oh, did anyone say it already?
35.
35. I apologize if someone already said that. Okay. So that's what the part of A that has nothing to do with B is right there, because this has something to do with B. Okay. What about, we could take a look at, that's probably not the best color. A complement intersect B. Well, is that the same thing? A complement, A, B complement. So this is the part of B that has nothing to do with A. So it'd be around here. Anyone tell me that one?
19.
19. Okay, so we see that these are not the same. But would you agree that that is the same thing as B intersect A complement? Would you agree with that? Can I flip the order around? Is that acceptable?
Yeah, it's the same.
So yeah, it is. It is. You can flip the order around. We saw that in I think one of the homework problems before. What about? Let's try.
I was actually going to mention that one of my homework problems had this, but it didn't let me choose the answer that was flipped. It said it was still incorrect. So,
Is that the one you emailed me about?
yes.
Okay. If hang out after class and we'll take a look at it.
Okay.
Yeah, I looked at it and it looked okay, but let's look at it again after class and see if that's the issue. Let's try this. I'm gonna write it a little differently. B intersect A complement intersect C complement. How many is that? And I would think of this as B minus A minus C. That's how I think of it. But it says B intersect A complement intersect C complement. How much would that be? B intersect A complement intersect C complement.
14.
14. Awesome. 14. This is the part that has a part of B that has it's just pure B. It has nothing to do with any of the other elements or the other sets. Okay, switch colors. What about this one? A complement intersect B complement intersect C complement. What does that equal? And everybody's a complement. They're all intersections. What must that be? What is the thing that all of the complements have in common? What's the thing that?
The empty set?
Nope, not empty. Not
Is
empty.
is it 19?
It's 19. Very good. It's this one. So because it is the all intersections, all complements, it's the thing that all complements share in common. It's this 19. It's the outside. This is the outside. So this is 19. Okay. How did my friend De Morgan in the previous lecture say that we could also write this? So this is also A union B union C complement. Okay. That's what my friend De Morgan said was true. Do you agree that that 19 is the complement of all of the union? Well, let's see. One of my friends also said that the union is 81 and that the universe is 100. The difference there is 19. So we see that that is true. So we see that De Morgan's law seems to be relevant and true in many, many different ways. Okay. Can I sneak some more problems on the right side of the screen? I'm going to try. So I'm on the top right now. What about the number of let's do B intersect C intersect A complement. What do you think that is? What does B and C have in common with not A? B and C, but not A. What number would that be?
5.
5. Very good. That is this 5 here. That's how we could write that. That's the part of B and C that they share that has nothing to do with A. So that would be that 5 there. Awesome. Is there another good one? I don't think we did this one. B complement intersect C complement. Could we do this one? B complement intersect C complement. So my friend De Morgan said that you could rewrite this as B union C complement. Does that help answer the question? These are equivalent statements. Or they should be. Let me double check. B complement goes to B, intersection goes to union, C complement goes to C, and then all of that becomes a complement. Okay, so these are equivalent statements by De Morgan's law. Can we identify what this is? What would this be? B union C is anything.
Is it
12 and what else? Yep. And so what does that come to?
31?
31, yeah. Very good. Okay. I probably have room for a few more. Let's do. Gotta do ones I haven't already done. I don't know. That's probably. Is that enough? Okay, so hopefully, this practice, this little game here, is good practice. I hope it seems approachable. We seem to be getting them every time. I did mention De Morgan's law a lot. So I'm going to refresh what that meant. De Morgan's law stated, and you can write this in many different ways, but A union B complement is equivalent to A complement intersect B complement. Okay. So how do you remember that? It's kind of like distributing in algebra. It's like distributing the exponent, but you're distributing the complement. So everything becomes the opposite. So then it becomes not A. The opposite of the union is an intersection, and the opposite of B is not B, the complement. So you can go back and forth. You can also write A intersect B complement as A complement union B complement. So that's saying that the opposite of the intersection is the union of the complements. Okay, the union of the complements. So that's De Morgan's law. It comes up a lot. It will definitely be on the quiz. It'll definitely be on the test in some fashion. It's one of the core things that we learn in chapter 1 is De Morgan's law, so it'll certainly be covered. And if you add this notation, which is what we're doing in this section, we're adding this notation of the number and the diagram and putting those ideas together, all of those statements are still true. So De Morgan's law is still true, even if you're considering Venn diagrams or sets that have numbers in them, it's still true. This is still a true statement. Something that's also still true that we need to keep in mind is the union rule. The union rule, I didn't mean to do that last part. The union rule states that the number in A union B is equivalent to the number in A plus the number in B minus their intersection. Okay, that was the union rule. You can rewrite the union rule using using subtraction, but using algebra, you can rewrite it and call it the intersection rule. So you can rewrite that union rule. But I state that this is true for all sets. This must be true for all sets, no matter what. And this is true for our Venn diagrams with numbers inside them as well. So it's true for all sets. So of course it's true for these sets as well. So you want that most certainly in your notebook, the union rule, which we went over last time, but it's going to show up in the homework again. So definitely have that at your disposal. Let's see, we're doing good on time. We'll also be talking about disjoint sets in this section, but we talked about that at the beginning of class in our review over the homework. So that should be fine. Okay. I think for the most part, we are prepared to tackle the homework, but I'd like to ask, are there any questions before I move on of anything that I've stated so far? Is there any questions?
No, I don't think there's any questions.
Okay. And maybe I'll ask a question. Would anyone like to see an example of this again? Would anyone like to see an example of the union rule before we move on? Yeah, okay. Good. So I will, I guess we could just come up with our own example. Let's come up with an easy example that we can demonstrate that this has to be true for all sets. Okay. So I'm going to try to show that the union rule is true for all sets. Okay. Let's come up with some numbers. I don't know. 2, 5, 7, 3. Okay. This should be easy stuff. If the first one worked, this has got to work, right? So let's see. Let's find. So the number of A would equal 2 plus 5 is 7. And the number in B would equal 5 plus 7, which is 12. And so the union must equal 12 and 2 is 14. And the intersection is 5. And I guess just for funsies, the outside is 3. And so we have a complete system here. We should be good. Let's check and see if that union rule is true. So the claim is that for even these sets, that the number in the union is equivalent to adding them together, but subtracting their intersection. That is the claim of the union rule, that it's true for all sets. Let's see if it's true. So if I fill this in, that would be 14, assuming I did my arithmetic correctly. 7 plus 12 minus 5. Is that true or false? 7 plus 12 minus 5. I get 14. So it seems to be true. It's supposed to be true for all sets. So I'm happy to see that it is true. We can also show it the other way. A intersect B equals the number in A plus the number in B minus the union. That's just swapping them out. So we've technically already shown that this is true, and we can probably believe that algebra is true, but I want to demonstrate what this means. So their intersection is 5. A is still 7, but not this 7, but this 7. B is 12, and then we'll subtract their union, which we found to be 14. So I claim that 7 plus 12 minus 14 is 5. Okay, so I claim that that's true. For a little bit of a trickier problem, we could do things with complements. We could start working with complements. So you could find a complement, which would be 7 and 3, which is 10. And then you could see, does this still work? This is a little bit trickier, but you could demonstrate, would this still work with a complement? So for instance, does a complement intersect B equal the number of a complement plus the number of B minus the number of a complement union B? And you could see, is this true or false? And you could kind of incorporate these complements and see if you can find one that breaks the union rule or not. But you know, it will require more, probably more patience to do something like that, because usually when you introduce complements, it gets more complicated, right? It gets more complicated. Let's see if we can do it. So A complement intersect B, that's the one I always think of as B minus A. That's what I always have. So B minus A, what is that? That's the part of B that has nothing to do with A. And so I think that would be this particular 7 here. A complement, I believe, is 10 because it's this 7 and this 3. So I believe that this is 10. I still believe that B is 7 plus 5, which pretty sure is still 12. And then the hardest one, I think, is A complement union B. And I should probably slow down just a little bit and talk about what this is, because there's a little bit of confusion sometimes with this. So remember that union means you're adding sets together. Everyone that's included gets added in. So A complement union B, everything gets added in. So A complement is this 7 and this 3, okay? But B is unioned with A complement. So everything in B gets added in. So this A complement union B is this 5, this 7, and this 3. So I ask you, does that make sense of where I'm getting that from? So I claim that that's 15. Does that 15 make sense? That can be confusing because students say, well, no, that's A complement. Why did you add a piece of A back in? You shouldn't do that because it's A complement. By definition, A complement is not A. So why are you adding part of A back in? I'm adding it back in because it has to do with B, and this is the union rule. And union is less restrictive. Union is less restrictive than intersection. So it's A complement or B, whatever's most, right? So when you talk about this, you're going to add a piece of, ironically, you're going to add a piece of A back in because that has to do with B. Okay. So I think if I did it correctly, that 12 and 10 minus 15 equals 7 by no coincidence. Okay. So I'm also claiming that you can use the union rule with complements too. You can add in complements and the union rule still works. It is still true, even though in the general form it has no complements there at all. So you could mix this in many different ways. Okay.
But when you're doing the union B, you're not double counting the 7, right? All right, I just want to make sure.
That's why I'm subtracting the 15. So I'm taking the 15 out. Otherwise, I would be overcounting because for the A complement, I have 7 and 3. For B, I have 7 and 5. And then I need to take away this. So I need to take away 5, 7, and 3 away. Otherwise, I'm overcounting. So that's why we take it away. So something to think about. I think if you're faced with a problem like this, if they didn't give you the diagram, they just gave you this information, I think it's worth your time to fill out a Venn diagram, especially when you're learning this for the first time. If you can draw a picture, it will really help you understand what the problem's asking, even though it might be a slightly more time consuming. Okay, any questions?
No, I don't think so.
Okay, so I'm gonna show the homework and we can kind of talk about what the homework's asking, and I'm going to give pretty good hints, and I'm going to at least completely solve one of the problems step by step, or at least, yeah, I'll do quite a bit. So let's see. So this is homework 1C. That was section 1C that we just talked about. And so here's the homework. We have 15 problems to tackle. Let's take a look. Okay. So the first problem says that A and B are disjoint subsets of the universal set, that the universe is 30, that A is 8, and that B is 5. Find the number of elements in the following sets: A complement and A union B. Okay. So we absolutely have to understand what the word disjoint means, or we cannot solve this problem. So if A and B are disjoint, that means their intersection is the empty set. Absolutely has to mean that. You could also say that the number of elements in A and B is equivalent to 0. That's, you could say that. Okay. I don't know if it would, make you any friends at a party if you said it out loud and you said, well, if you have two disjoint sets, it means their intersection would equal 0, but it's true. Okay. So if A equals 8, B equals 5, and their intersection equals 0, because they're disjoint, I can fill that in. I can fill in 0. And it's always good to fill in the intersection first if you can. You can't for every problem, but for the problems you can, it's a good place to start. So that makes this 8, that makes this 5. The universe is 30, so we have 30 minus 5 minus 8, which is 17. Okay, I think I know everything about this. I just have to answer the questions. So what is A complement? A complement is anything, it's not A. So that would be 17 and 5. That's the 22 there. A union B is just this 8 and 5. And I can just put those together because I know the intersection is 0 because they told me that it is disjoint sets. So there you go. That's how I would do the first one. You will have varying, your questions may vary a little bit, but that would be the basic idea. Okay, very similar, but not exactly the same. A and B are disjoint, so that means the number in A and B is 0, or you could say that A and B are the empty set. The universe equals 20, A equals 3, B equals 4. How many? Find the number of the elements in each set. So what is the intersection? Well, it's 0. They told me because they said it was disjoint. What is B minus A? B minus A. Well, B minus A is just B because they're disjoint. They have nothing in common. A is 3, B is 4. Since they have nothing in common, B minus A is just B. And then what is A union B complement? Okay. So I probably wouldn't use De Morgan's law to rewrite this. I think this is easier the way they wrote this. This is what is this area here, the outside. What is that? We have 3 and 4, which make 7. So we just need to take 7 away from this 20. And so we get 13. This must be 13 there. Okay. So hopefully that seems easy enough. Okay, in this problem, not too bad. It's just, this is kind of what we did together. And I mean, we'll all have different problems. I know I know the pictures are annoying. So, always try to keep clicking the picture, refresh the page until it shows up. It will eventually show up. But for these, you just need to add them together. So if you have A, you just need to add these numbers together. B, same thing, add them up. C, add them up, and then add up all of the numbers to find the universe. So hopefully that won't be too challenging. Okay, this is very similar. Add 11 and 9 to get 20 for A. B, 20 and 9 make 29 for this B over here. B complement would be this 11 and 5. And then A union B complement. This is what we were talking about earlier, which could be confusing when you have the A union B complement, because you're adding a part of B back in, and that can be confusing. But all of A and then all of B complement, so that'd be 11, 9, and 5 there. That's where I would get those. So that can be confusing when you're dealing with union, because you're adding a part of the B back in, and that can be confusing to students. But hopefully after after me talking about it, it won't be too bad. Okay, let's talk about these. So we have A complement. Well, that's any number that has nothing to do with A. So that would be the 14, 11, 12, and 6. That's the part that has nothing to do with A. A union B, that would be anything in the red circle, anything in the blue circle, and we don't want to overcount anything. So you just count things one time. So 7, 14, 8, 10, 12. I got 62. So, and your numbers will vary, but be sure that you're not overcounting. We don't want to count this 8 twice because it's in both of them. You just count everything once. B intersect C complement, I think of as kind of like B intersects C complement. I think of this as B minus C. That's how I think about it. So B minus C is the part of B that has nothing to do with C. So this orange circle here is our C, and so that would be this right here, that 10 and 12 would give me that 22. These right here. Okay. And for this last part, we have A complement intersect B complement intersect C. I know we did something very similar in the lecture portion, but I would think of this as C minus A minus B. It's the part of C that has nothing to do with the others. So that would be that 14 right there. That's how I think about it. It's how other textbooks write it. WebWork never actually brings up the idea that A complement intersect B. It could be thought of as B minus A, but I think of it every time. That's how I think about it every time. So I hope it helps to see that. Hopefully it's not confusing. Let's see. Okay, what about this one? All right, similar but not the same. We have A union C complement. This one that could be a little confusing because of the union, you're adding a piece of C back. So we want all of A. We want all of A in ours. And then C complement. We want all of C complement. So that'd be this 12 here and this 12 here. So we're just subtracting from the universe these two numbers, or we're just putting these numbers together. That's how I would find it. Okay, back up a little bit. Different color. A union B intersects C complement. This has parentheses. When you're dealing with parentheses in math, it's, I think, always important to evaluate the parentheses first, even if you're talking about sets and logic. So A union B, what is A union B? A union B is anything that's in A, anything that's in B. So that's these numbers. And this bluish green color here that I circled, that is the A union B, that's the parenthesis here. Now, what does that have to do with C complement? What does that share with C complement? So I have all of these numbers here, and it's C complement. So I think of it as taking C away. I think of it as A union B minus C. So I do have some C numbers here. I don't want them. So I think it's these numbers. Maybe not the best color to pick. There you go. So I think it's these numbers here, which would be A union B minus C. We're taking C away. We're taking C away. Okay. And then A complement intersect B complement intersect C complement. That is the outside. That's the outside. Okay. Now, A complement intersect B complement intersect C complement. Our friend De Morgan says you can say A union B union C complement. It's the complement of anything that's in those circles. It's the outside. It's the outside. Okay. Okay. So I hope that helps when you're working on your own problem. Let's talk about this one. X and Y are subsets of the universal set. X intersect Y complement is 14. Their intersection is 13, and Y is 14. We want to find X, and we want to find X complement intersect Y. So if I was in your shoes, the first thing I would do is try to draw a picture. I think that's going to be the easiest way for you to be able to solve the problem. You might not have to, but I think if you do, it will save you having to redo it. So if you can, you always fill in the intersection first, and I can in this problem. So this is 13. I can fill that in pretty easily. X intersect Y complement. I always think of that as X minus Y. That's this part here, and they tell me that that's 14. They tell me all of Y is 14. All of Y is 14, but I already have 13 inside Y. All of Y is 14, and I already have 13 counted for, so I think this is 1. Okay. So how much is X? Well, X would be these two together, so you get 27. And then how much is X complement intersect Y? That's the Y minus X part. That's 1. That's just 1. Okay. So hopefully that makes sense. What about this one? The universe equals 60, X equals 21, Y equals 16, and X complement intersect Y is 7. You want to find the outside, and then you want to find X complement union Y complement, and you'll find that that's the complement of the intersection if you use De Morgan's law. X, Y. So the universe equals 60. X equals 21, Y equals 16, and X complement intersect Y is 7. That's Y minus X. That's here. So they tell me that this is 7. I know that all of Y is 16, so that must mean that the intersection is 9. Okay. The intersection X intercept Y must equal Y minus X complement intersect Y. That's probably a little confusing, but I'm just saying that's where I got the information. Then I know all of X is 21, and I know that just part of it is 9, so the remaining must be 12. Okay. And what else? What else can I say? Well, I know 12, 9, and 7 add up to 28. X union Y equals 28. And if all of it equals 60, I could say that this equals 32. So there's my 32 is the outside right there. And what about x complement union y complement? Well, if you use De Morgan's law, that's x intercept y complement. It's the opposite of the intersection. It's everything but this 9. So it's 12, 7, and 32, which I claim is 51. So that's how I would do that problem. Hopefully that helps. This one tells you about the union rule. So the first part is just it explaining the union rule to you. Just a little refresher there. But the actual problem says that A equals 14, B equals 5, and A union B equals 17. You want to find the intersection, and you will need the union rule to do this. We can use this version right here. So the number in A intersect B for my numbers would be 14, 5, minus 17, which I claim is 2. Okay. So the first part's just telling you the textbook union rule. Don't forget it. You'll need it for this problem. And then at the end, it actually gives you the numbers, and you will evaluate that. So yeah, hopefully that helps get you started on problem 9. J and K are subsets of the universal set. J equals 12, K complement equals 5, and J union K complement equals 15. Find J intersect K complement. This is not like, we've never done a problem like this together before. We've never worked on something like this. So let's think about how we can do it. It has a hint here. It says for any sets A and B, their intersection is the sum of them minus their union. So it's reminding us of the union rule here at the bottom in the intersection form. But how does that help us? Well, I mentioned in the lecture part that if you add complements, it is still true. The union rule is still true as long as you're consistent. So we're given J, K complement, J union K complement, and we're asked for J intersect K complement. So I think that it would still be true to say that J plus K complement minus J union K complement is still true, even though we're using J and K instead of A and B, and we're using complements instead of just standard. I believe that it would still be true. We're given all of this information. So this is 12, this is 5, and this is 15. So yeah, that's going to equal 2. Okay. So you can still use the union rule even if you're dealing with complements as long as you're consistent. Notice that K is always the complement. It would not be true in general to say J intersect K equals J plus K complement minus J union K complement. You can't have a complement on 2 of the 3. They have to be consistent. It has to be complements on everything. So if it's K complement, it has to be K complement for everything. Okay. So that is not true. This would not be true. So I would cross that out. I hope that helps. Get started on problem 10. Problem 11, we have some vendors. We have a word problem here. Let's see what we can find out. So of 35 vendors at the farmer's market, there are 10 that sell carrots, there are 14 that sell tomatoes. If 3 of the vendors sell both carrots and tomatoes, how many of them sell neither carrots nor tomatoes? So I would say we should try to draw a Venn diagram if possible. And we should also try to write out what our sets are. Like, what do we know? What do we not know? We need to kind of break everything down. So the whole farmer's market is 35 vendors. So I'm going to let the universal set equal 35. That's where I'm going to start. There's 10 that sell carrots. So I'm just going to say that C equals 10. 14 sell tomatoes. So I'm going to write T equals 14. And 3 of them sell both carrots and tomatoes. So if you let carrots be C and tomatoes equal T, then C intersect T must be 3 by the given information. We're asked how many sell neither carrots nor tomatoes. That's the outside. Okay, so that would be C complement intersect T complement, or you could write that as C union T complement, however you like. But that's what we're looking for. Let's see if we can draw a Venn diagram and try to understand what's going on. If I let this be the carrots and this be the tomatoes, always write the intersection if possible first, and I can for this because they gave it to me in the given information, so that's 3. Then the carrots are 10. We already have 3, so that would be 7. If you add these together, you get your 10 back. Tomatoes total 14. We already have 3 here, so the remaining would be 11. 3 and 11 make 14, so that should be good. And we just need the answer now. We're just looking for the outside, and we already have 7 and 3. We already have our 10. 10 plus 11 is 21. We're going up to 35. 35 minus 21 is 14. So I believe there's 14 out here, and that's the same 14. Okay. So that's how I would tackle that problem. It's always good to break every bit of information you know into pieces and see where you can go from there. Of course, it's easy when someone shows you how to do it. It's always hard when you don't know where to start. So that takes practice. Of the 36 vendors at the farm, there are 6 who sell carrots, 11 that sell tomatoes. If 20 of them neither sell carrots nor tomatoes, how many of them sell both? So I think this is similar enough where I'm going to leave it to you to figure this one out, okay? Because we need the practice, so it should be similar enough to at least have a start being able to do this. So maybe I'll back up. I'll save a picture of this one, and then you can try to solve 12 yourself. Okay. I want to mention something about this problem, problem 13. A and B are disjoint sets. If the universe is 18, A is 5, B is 6, find the number of elements. This is the Cartesian product that we learned about last time, Monday night. And remember, the product is just multiplication. It's just multiplication. So you can multiply just like before. So A cross B would be 5 times 6 for me. 5 times 6, and that's 30. So you can just multiply those numbers, and that is how many would be in that Cartesian product that we talked about last time. We don't have to actually find the Cartesian product. We just find how many elements are inside. Okay. The next one is A complement times B. Okay. It's not intersect. It's not union. It's A complement times B. We already know how much is in B, but how much is in A complement? How much is in that? Well, I know that A is 5. There's 5 elements in A. I know that the universe equals 18. So how much must be in A complement? Is anyone willing to say? Would anyone be willing to say how much would have to be an A complement? If the universe is 18 and A is 5, just forgetting totally about B for a second, how much must be an A complement? Oh, there's one in the chat. Let's see. 12. Close. Very close. How did you get 12? Maybe tell me that. How'd you get 12?
13. 13. I don't know.
13. 13. So 18 minus 5, right? So there we go. There's a complement. Now you can go 13 times 6, and I claim that that is A complement times B. Okay, and then A cross A is 5 times 5. So we don't actually have to find what the Cartesian product is. We don't have to enter it what it is. But we can find out how many elements are inside just from the given information. Okay. Now, A and B are subsets in the universal set. The universal set is 28. A is 11. B complement is 13, and A union B is 20. You just want to draw a Venn diagram and work it out. I think if the lecture has made sense so far, this should be fairly straightforward. I don't foresee any tricks or stumbling blocks. Just fill out your Venn diagram and things should go in order. This one is tricky. This is the last one on the homework. It's very tricky. There's a fully worked version in the discussion section, but this is a three set Venn diagram that you have to go through, and you talk about the vendors. There's already a fully worked version of the problem, and it will take some time to do this one. So this is probably going to be the hard one to do. Everyone will have different numbers, so that will be frustrating. But I would take a look at that. If you need the extra help, take a look at that fully worked version in the discussion section, and hopefully that will get you through it. But what you're looking for is it's like volunteer. It's like one of those taste test things where people are tasting different drinks, and so you have carrot, cantaloupe, kiwi, kale, raspberry, rhubarb, and people are tasting this. There's, in my problem, 190 volunteers that are tasting this. So certain people like one drink over the other. Carrot, 24 people preferred it. Kiwi, 32. Raspberry, 20. And then people that like more than one, I have 8 for my carrot and kiwi, 16 for raspberry and kiwi, 10 for carrot and raspberry. And then people that liked everything were 9. Okay. This is where I would actually start the problem. Okay. I'm just going to give some hints here, but I would tackle the problem this way. Okay. Because it gives you the information of all of them, I believe it will be easier to weed out instead of starting at the beginning, start at the end and go up, because you can fill out the Venn diagram in this way. Was there a question? I hear somebody's microphone. Is there a question? Nope, maybe not. Okay. So let's see. What do we have? I like to just do one letter because I'm dumb. So I'm gonna write carrot, kiwi, raspberry. That would be easier for me to do. And then all 9 people liked all of them. So I would start there. I would start with this 9. And I think that is the easiest place to start. So if you start with that, then you can work your way out. So carrot and raspberry is here. You already have 9. It adds up to 10. So there must be 1 there. And just keep going. Okay. But again, there's a fully worked version and a discussion. I want you to have the practice of solving it yourself, but hopefully that one will work out. If we need to, we'll talk about it next time, but that should be pretty good. I mean, you have a fully worked version and discussion. I just gave pretty good hints of how to start, so that should be enough to do it. Okay. So that is the homework. That is section 1C. That concludes chapter 1 of Finite. Are there any questions?